Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College London in the UK, and this is the new episode of the podcast Turbulence at the exascale. If you're not familiar with the podcast, we are trying to gather the view of the scientific community regarding the challenges and opportunity associated with exascale computing for turbulence research and turbulence simulations. So this podcast is part of the UK ExCALIBUR initiative, which is a 5-year program dedicated to software development and training to harness the power of supercomputers and exascale computers in particular in the UK. It is led by the Met Office, the UK Atomic Energy Authority, and the UK Research Innovation. And this podcast is also part of the UK Turbulence Consortium. So today we have a guest from the UK, from Cranfield University. His name is Takis Tsoutsanis. So good morning, Takis.
Good morning, Sylvain. Thank you for the invitation.
And so Takis is a senior lecturer in CFD, and his research expertise is about a lot of things, in particular high order methods for highly unstructured meshes to study complex turbulent flow, some adaptive mesh refinement techniques, some implicit large dissimulation technique, turbulence modeling, rounds, and so on and so on. So he is an expert in CFD and HPC, and so it's going to be great talking to him today. So my first question, Takis, for you is, can you tell us a little bit about yourself, where you are from, what you have studied, and how did you end up at Cranfield University?
Okay, thank you very much. So I'm originally from Greece, from the south part of the mainland of Greece. And I came to the UK when I was 18 years old. I did my MA in aerospace engineering at the University of Liverpool. Then I returned to Greece and I became a cadet reserve officer in the Hellenic Air Force. And then I returned back to the UK, did my PhD at Cranfield University, dealing with development of high order unstructured methods. Then I returned again back to Greece for 2 years, working in the national flag carrier airline as an airframe development engineer. And then I returned to academia, spending 1 year in Cyprus, working in numerical methods development for climate and weather forecasting. And then I returned to the UK back for good in 2012 at Cranfield University, dealing with unstructured methods and further evolution of the work. And yes, since then I'm here at Cranfield. Yes.
Great, and thank you. May I ask you, how did you become interested in turbulent flows and in CFD and high performance computing?
Yes, so I was, let's say, always fascinated by CFD, being an aerospace engineer. So we had introductory modules at year 1 and 2, and I was always fascinated about analysis of these complicated flows for aeronautical applications. So it came quite natural to pursue a PhD and develop methods for compressible flows. And in particular, dealing with unstructured methods that were, let's say, solving quite a lot of our problems in terms of fast turnaround times for complicated geometries with an automated process. But the numerical methods were not, let's say, up to the task for achieving very good accuracy for this type of geometries. And I think when I started my PhD, I realized that you had to become a software engineer, an applied mathematician, a physicist, all sort of different, let's say, skills that I had to develop. And back in the day in 2006, I think it was, Cambridge and Cranfield were sharing the same HPC back then. And it was one of the few UK HPCs that was in the top 500 list back then. So everyone was, let's say, encouraged and fascinated to learn how to use the system. So from day one that I started developing these methods, I hadn't run a single serial simulation, or parallel was there from day one. So yeah, that was, let's say, the beginning of the journey.
Great. And my next question is, so you have been spending lots of time in Greece and in the UK, and you have been now in Cranfield since 2012. I was wondering, what's the best thing about your job, your current position, and about working at Cranfield University?
Yes, there are a lot of things, to be honest, but some of the most important ones in terms of our research is that we get to test quite a lot of interesting research ideas and research directions at low TRL level with the individual research projects of our MSc in CFD students that can later on let's say, form the foundation of bigger projects and collaborations with industrial partners that Cranfield has been really strong for a number of years with, in particular, the aerospace, automotive, and motorsport sector. So the other thing is that there is a long-standing tradition and legacy in the department on developing numerical methods for compressible flows, starting from the pioneering work of Phil Rowe with his Riemann solver and Tito Toro with his Riemann solver as well, that have established, let's say, this mentality and philosophy of developing methods ourselves here in the department. And this philosophy remains really strong up to this date, since there were a lot of students of them that became academics here, and we were students of them. So there is a tradition in this front, and we're really passionate about developing and applying methods for compressible flows, in particular, because they're closely tied to the aerospace sector. So this is something that we really enjoy.
Excellent. Thank you very much.
Yeah.
Right. Can you briefly, we are going to talk about them in more detail, but can you briefly describe what research project you are currently working on, so we have an idea of your activities?
Yes, they span from the development of high order methods for multi-physics modeling, lately for landing gear systems, this is a work funded by PSRC and Airbus. There is another project on multi-fidelity, multi-physics modeling, funded by Innovate UK and Airbus UK. A work on high order implicit large eddy simulation methods for industrial scale aeronautical flows, funded by EU Horizon 2020 programs. Another one with hybrid discontinuous Galerkin finite volume methods for aeronautical flows, and of course parallelization, optimization of parallelization and scalability of the code under several EU funded projects. We just currently finished the third project related to the optimization of the code and the methods that we develop. funded and supported through PRAISE experts. So yeah, more or less this is what I'm doing at the moment.
Great, thank you very much. Right, so my next question is about the solver that you have been actively developing recently, called UCNS 3D. So I've seen a lot of nice visualization on Twitter and in your recent publications. So I'm really curious to know a little bit more about this solver. So can you tell us a little bit about the numerics and the parallelization strategy in UCNS 3D?
Yes, so it started when I began my PhD in 2006. So it was, let's say, initially a linear advection solver running on 2-4 cores, and it's currently running on hundreds of thousands of cores, and running implicit large eddy simulations for 250 million cells. So there has been a very long journey to reach up to this point, but let's say the core aspect of the code is to make it more accessible to everyone to develop finite volume methods for unstructured grids, for multiphysics modeling, for turbulent flows, for shallow water equations, numerical weather predictions, you name it. So we have tried all sorts of different things. In terms of numerical methods, we have started with traditional muscle schemes, and then we moved to Wino schemes that we introduced for hybrid unstructured meshes. They were very expensive and they still are very expensive, so we moved towards improving the performance and the accuracy of muscle type of schemes, so we were able to achieve higher than third order of accuracy for muscle type of schemes. And lately we introduced a more kind of efficient and robust variant of the Wino schemes called compact or central or cool Wino schemes, as they are called. But along the lines, we have used established, let's say, Riemann solvers, time stepping schemes, implicit, including dual time stepping, that really is beneficial for unsteady simulations, and especially when we want our time step not to be restricted by the CFL restrictions, and turbulence models, so Spala-Tarmaras, K omega, multiple and single rotating reference frameworks. What else we have done? In terms of parallelization strategy, so the parallelization takes place within the code, so the domain is partitioned by the par-metis algorithm, and the key communication requirement, let's say, or overhead, in particular for explicit time stepping schemes, is just communicating the extrapolated reconstructed values at the interface between cells. Because initially someone might say that these let's say hollow cells of the stencil and so on might of these finite volume large stencils might pose quite a lot of communication overhead, but we have managed to alleviate that with the latest compact Wino schemes. And finally, the main flexibility is that it operates with the most popular grid formats like MSH formats, StarCD, UGrid formats that are used in the aerospace sector quite a lot. And TechPlot, ParaView style of outputs. And yeah, I think more or less we have developed the code in Fortran mainly. We use some small sections of C, and then the plan is to introduce some Python just to glue certain modules together. So yeah.
Thank you very much. Very nice. And I will, of course, add a link to there is a nice website with a lot of information and GitHubs and everything. So I will put this link when I will post about this podcast. You briefly mentioned that you are working on the new generation, I will say, of Wino schemes. So can you tell us a little bit more about what those new schemes are providing you? I mean, you said better performance, higher accuracy. Can you tell us a little bit more about that?
Yes, so I think the original implementation of the Wino methods that we had for finite volume was that they had these large directional stencils, and that was introducing quite a lot of let's say bottlenecks in terms of the parallelization, because there were some large directional stencils that they were propagating across the interfaces between processes. So we've managed to introduce a new variant with a colleague, Michael Doomser, in the University of Trento, where we got rid of these high order directional stencils and we replaced them with lower order directional stencils. And in a sense, what we are doing is in the presence of some spurious oscillations or some non-smoothness in the solution, we blend the lower order directional stencils with the central high order stencil, something that was traditionally done in finite difference, finite volume structured kind of codes. But for the unstructured methods, it was the figuring out how to employ correct, let's say, linear weights for doing something like that. It is, let's say, a variant that has an amazing potential, and it has started being used for different communities, including finite element methods, because one of the, let's say, pioneers in this field of Wino schemes, Zhiguan Su in particular, that has introduced Wino schemes, Rungakuta DZ schemes, and so on, is referring, and he has a famous quote saying that eventually for high resolution methods, you will need information from neighbors of neighbors. So I think this, let's say, variant of compact or cool or central Wino schemes, as they are called from various researchers, is that they are very robust and they are quite efficient, and they can easily be used for other frameworks to fortify their non-oscillatory properties, because the directional stencils that you just deploy with these methods are very compact. So scalability or the communication overhead of any framework is not, let's say, adversely impacted by them. Of course, as with every essentially non-oscillatory schemes, and especially the Wino variants, dispersion and dissipation analysis is not straightforward for unstructured methods. So this is something that we are really working on with a colleague from Spain and one from Hong Kong to try to figure out how we can, let's say, assess the methods for implicit large eddy simulation in particular, because dissipation control for Wino schemes is pretty straightforward, but dispersion control is really tough. And we have one additional, let's say, parameter that complicates the situation for unstructured meshes. It has to do with the unstructured mesh topology and the quality of the mesh at certain regions that might, let's say, activate the Wino methods falsely. So we have to deal with these sort of things. But yeah, this variant is really robust, and we have been using it for the past, let's say, year throughout all our work.
Great, thank you very much. One of the recent application I've seen with your code is hovering rotors with and without ground effect. And I was wondering, how are you dealing with moving geometries with your solver?
Yes, so we started, the main motivation for this work was that we have seen in the past that when we were running some run simulations with the code, we saw that there were some benefits when we were using moderately high order methods, so third order methods or fourth at most, were offering some improvements in the accuracy of our prediction, even for run simulations. So we said that we could give it a try for hovering rotor applications, and in particular for steady state ones, because the framework that we are using, which is the multiple reference framework, is really suited for steady state simulations. So we tried to avoid the sliding mess and overset messes because it would complicate the picture back then quite a lot. So we said we are going to stick with the multiple reference framework. And what we have found out in this latest work that we did is that for multiple reference framework in particular, they seem to benefit more than we expected from slightly increasing the spatial order of accuracy. In particular, when we are moving into close proximity to the ground due to the interaction of the wake and the vortices with the ground itself. And we compared against experimental and previous computational work, and we got really encouraging results. Now, the next step will probably involve either abandoning the MRF altogether to move towards unsteady and sliding or overset meshes, or figuring another way to deal with unsteady problems or rotating flows. But yeah, that was the main motivation behind this work. So yeah.
Thank you very much. Right, so now I have a few questions about exascale computing, and my first question is: so you say, well, you are already running very large simulation. You mentioned a 250 million mesh node. So if I give you access to an exascale computers tomorrow, what will you be able to study that you cannot do at the moment because of computational restriction? What would you go for?
Yes, so we have been lately doing some implicit large eddy simulation for these high lift aircraft configurations. And I think the first thing that we would go for was to further increase the resolution, because implicit large eddy simulation initially was conceived as a poor man's LES, but nowadays it's receiving more momentum across different frameworks. Flux construction, DG, finite volume. And what I would use in exascale is to increase the resolution, possibly look at landing configuration and steady simulations of aircraft in close proximity to the ground, which is something that we haven't done in the past, to see how the aircraft interacts with the landing runway, and of course we're talking about scale resolving simulations. But I think in principle, in terms of the code, we're able to do it. In terms of post-processing and big data management, there are a lot of challenges that so we haven't, let's say yet thought how we're going to address. But yeah, this is what we will do.
Good. And a follow-up question: do you think that the code that you have, UCNS 3D, is going to be ready for an exascale computer, or do you think you will have to rethink I don't know, the parallelization strategy or maybe, you know, various things. What do you think it will scale well beyond what it is doing now, or do you think you need to rethink a little bit?
I think for the very high order methods, it will scale really well. We have managed to go up to, let's say, 90% parallel efficiency while having less than, let's say, 20 or 30 cells per core. So increasing the number of cores, the number of elements per core, which implies increasing the number of processors and running bigger simulations is straightforward. I think one of the challenges is post-processing, so vast amount of data and how we're going to deal with that. We have done some preparatory work for real-time visualization in the code with the ParaView Catalyst library. We have tried it up to, I think, 128 CPUs just to figure out how it is working. And I think this is the front that we need to do more work. But with regards to the lower order methods, in particular for the ones dealing with runs, turbulence models, and implicit time stepping, I think a lot of work needs to be done to harness the power of the new exascale supercomputers, because these methods do not scale that well. But on the other hand, the productivity for this kind of simulations will increase dramatically, because we are going to have more simulations in 24-hour period running, which might be the only goal out of this exascale system for at least these runs simulations.
Excellent. And a quick small question: are you interested in GPUs? Are you going to look into GPUs or not yet?
Yes. So there has been an encouraging, let's say, change in the landscape in terms of the latest OpenMP variant, where we started, I think it was 4 years ago, where we switched from pure MPI to MPI and OpenMP. And lately they have included in the latest OpenMP GPU offloading, that it is supported by, I think, certain GPU vendors. So this is something that we will be looking forward, because once you have an OpenMP code already working and identifying the hotspots and picking up which sections to offload to the GPU, I think it is quite natural to do so. In the past, where it was, let's say, closely linked to certain programming interfaces like CUDA or other, let's say, platforms, I think it required quite a lot of investment in time and was not, let's say, our highest priority. But nowadays, with these new features and capabilities of OpenMP, I think it is going to be easier for everyone to offload certain things to GPUs. It might not get the maximum out of the possible performance that they can offer, but again, it is a welcome addition for everyone dealing with scientific computing and HPC in particular.
Great, thank you. My next question is, so you have been now well established in the UK since, let's say, 2012, and I was wondering, from your point of view, do you think the turbulence community and the CFD community is ready to move to exascale computing, or do you think there is still a lot of work to be done?
I think there has been a lot of work in several codes in terms of scalability with the likes of OpenSBLI, Compact 3D, PyFR, Saturn, Nectar++, you name it. I think that there might be some work required for the modeling aspects a little bit, because what we have seen is that once you calibrate certain methods with techniques that were the state of the art and popular 10 years ago. Maybe the fact that you are going to have access to exascale computer, you can afford, let's say, more accurate methods and so on, which might imply that you have to revisit and recalibrate certain modeling techniques for turbulent flows. But overall, I think the majority of the UK, let's say, CFD codes are well suited for exascale. It is just some incremental, let's say, improvements that might be needed in terms of post-processing, pre-processing, which is, let's say, a challenge not only for the UK turbulence community, but for everyone dealing with HPC in general. So yeah, this is my view regarding that.
Excellent. Okay, I have two more questions, and they are highly hypothetical questions. So it's my next question is about the hardware, and you might not have an answer to it, but I was wondering, are you happy with the hardware that you have at the moment to run your simulations, or if you could, you would like to change things? So, for example, like more memory or more compute power, or a different network, or what's your view on that?
I think that the change from the previous Archer variant to Archer 2 has been really impressive in terms of the hardware. And I have tried a similar system for 6-7 months on HLRS, the Hawk system, which has more or less the same architecture as Archer 2. And from day one, I was amazed by the hardware itself, because you can, let's say, it encourages a lot to the hybrid programming model of MPI and OpenMP. And we managed to get quite a lot of performance out of this system. So I was really impressed by that. And the fact that the Archer 2 has moved towards GNU compilers and open, supporting more the open access model has been a welcome addition. And I think that I wouldn't require anything more at the moment. Of course, more nodes are always welcome, but once the full system is up and running, I think that will be a major improvement compared to the previous system. We are already doing pretty amazing stuff with the 4 cabinets that are installed there. So yeah.
Excellent. Great. I have one last question for you. So we are talking a lot about exascale computing, and I was wondering if you have an opinion on what's going to happen maybe in 15, 20, or even 30 years. Do you think we are still going to be working with the same hardware? So, GPUs with more memory, more energy efficient, and more power, or do you think we are going to have to rethink everything, and we are going to see a revolution in terms of hardware?
I think there are two things that are going to happen. The first one is going to be more of an evolution kind of thing, which is related to the new kind of architecture of chipsets, where you can see that they have some faster CPU, faster cores, some slower cores. They throw some AI units, as they're called, in the mix. So I think because software and hardware go hand in hand, you might see an evolution where you have certain aspects of these codes that they are ported, they are offloaded to the faster cores, certain things that stay to the slower cores or the traditional CPU cores. And the AI will probably monitor certain things while the simulation is running and making some decisions in real time. So this is what I consider to be a natural evolution of things. I think the other aspect, which is the revolution, I think that if quantum computing catches up and there is a revolution in terms of how we can end up using this technology, then this might mean that we are again on square one and starting to rethink how we're going to harness all this computing power. So I'm keeping an eye in terms of all the hardware evolutions and what is happening at supercomputing conferences and programming models and software. But these quantum computing, I think, if at some point is going to be used in our sector in scientific computing, I think it is going to be a game changer for everyone.
Excellent. Well, thank you very much, Takis, for your time and for your input. It was very nice talking to you and to learn more about your research activity and to learn more about UCNS 3D, which, as I said before, I will put the link. It's a very nice flow solver for compressible flows.
Yeah. Thank you very much, Sylvain. Thank you.
No problem. So thank you very much, everyone, for listening to this podcast. As usual, I will be posting the links on Twitter. It's UK Turbulence in one word, and you can also find all the links on YouTube and SoundCloud on the UK Turbulence Consortium website. Just Google UK Turbulence, and you will find us easily. So thank you, everyone, for listening to this podcast, and hopefully we will see you soon in the new episode.